Welcome to day 3 of ISFDB. Today we're going to be talking about line rasterization and triangle rasterization. So, as I defined for you guys before, rasterization means putting dots on the screen. So, let's scroll down a little bit here. So, let's say you've got a point, you got another point, you got a screen that's full of pixels, and you want to draw all of the points from one point to another point. How do you do that? What do you think? This is at location, I don't know, 10 across and 20 up. And this is at location 12, 13, 14, 15, 16, 17, 18, 19. This is at location 19 across and I don't know, 24 up or something. Just eyeballing it. How would you write a for loop? Starting here, going to here, filling in all the points in between. Find the slope and draw along the slope. Okay. So the rise over run for this, the run is 9, and the rise is 4, or maybe we'll do it the other way. 4 over, the slope is 4/9, right? So as we go to the right, we travel 9 to the right and 4 up, so the slope is 4/9, right? So if we remember algebra, y is equal to mx plus b. So what we can do, one trick that I like to do just to make the math simpler is whenever I do something like this, I like to just kind of adjust everything to be at the origin. So rather than this being 10, 20, I subtract 10 and 20 and make it 0, 0. And then this guy just becomes 9, 4. Okay? X is equal to 9, y is equal to 4. That makes sense? Makes the math a lot easier. Right? You don't have to do anything. Just remember when you're finally outputting the pixels, you've gotten that written down somewhere, right? Yeah, so you've written down somewhere you're actually at 1020. So when you output 1, 1, it's actually 1121. But for doing the math, making the math easy, this is actually 1924. We'll just kind of ignore that for now. Make the math really easy. We start at the origin every time. Okay. So, so we do a for loop. So we just say for each column, for each value of x, right? So we've got 9 x's in between here, starting at 0, going to 9. So the for loop will look something like this, right? For x equals 0, x is less than or equal to 9, x plus plus. That's horrible and impossible to read. Let me try that again. X plus plus. Draw a pixel, and I'll tell you how to do that in a bit. Draw a pixel at x location, and the y location is going to be the x location times 4/9, right? So the slope is 4/9, right? We're going to have to store that in a float. Don't store that in an int. If you store it in an int, you're going to get 0, right? So m times x, right? And then that'll work, right? Collins, do you understand what we're doing here? So we're saying starting at this column, we're going to draw a pixel at x is equal to 0. Remember, we're going to adjust this. We're going to put the 10 and 20 back in somewhere. So that's probably going to be passed in secretly. But, we're going to draw a pixel at x is equal to 0, and x is equal to 4/9 times 0, which is 0. And then at x is equal to 1, this is going to be 4/9 of the way up, which is 0. So when we actually draw it on the screen, it's going to look like this, right? Because they're pixels, they're whole numbers. And then when we go to x is equal to 2, well, that's still 0. Okay. And then we come here, and x is equal to 3. So y will now be equal to 1. Here, let me draw this in a different color. Use galaxy colors or something. So this is the line we kind of want to draw. This is the line we kind of get out of it. It goes 3 horizontal, then it goes up 1. And now here at x equal to 4, 16/9 is still at 1. Haven't quite hit 2 yet. And then here we're at x is equal to 0, 1, 2, 3, 4, 5, 20. So y is now 2. And then this is going to be 24, so it's still 2. 28, so it's now 3. 32, still 3. And then 9, 36, and then it hits 4. Okay, so this is the actual line we get out. It's going to look like this. Horizontal line, up, horizontal line, up, horizontal line, up, horizontal line, and up. That's the line that's actually going to get rastered to the screen, and that's what rasterization is, right? So rasterization means I want to put a line on the screen. Okay, well, put the pixels on the screen. That's rasterization. It's a big word for a simple concept. So, but we got a problem here, right? Which is our line's going to look kind of weird and jaggedy, right? Like we have 3 in a row here, then 2 in a row, then a 2 in a row, then 1, right? Like that's kind of weird, you know? And if you actually color this in, you have a bunch of white pixels, you know, like that. And so there's some algorithms that will measure how much fraction you have, right? So like when we were here, this was 8/9, right? And so it means it's 1/9 here, and it's 8/9 up here. And so it would draw 8/9 of white on the top pixel and 1/9 of white in the bottom pixel. And so you would get this anti-aliasing effect where it would shade between the two pixels that it kind of encompasses, right? Because if you have a pixel kind of in between 2 pixels, then it'll shade kind of smoothly between them. Does that make sense? So you kind of look at the fraction, right? Do you understand what I'm saying? Like Collins, like here, 1, 2, 3, 4, 1. Like for this pixel here, there's 2 pixels it could be. It could be this one if you round down, or it could be this one if you round up, because we're at 1, 2, 3, 4, 5. We're at 20/9, right? That's the vertical location, 20/9, which is 2 and 2/9. Eta fractions, right? 20/9 is 2 and 2/9, right?
What?
20/9 is 2 and 2/9, right? 20/9.
20
20 over 9.
20 over
20 over 9 is 2 and 2/9, right? So that means we're on the second, we're on y equals 1, y equals 2, we're on y equals 2. And then we're 2/9 of the way to the next row. And so for this guy, he's gonna get 7/9 of the pixel color, and this guy's gonna get 2/9 of the pixel color.
Yeah, it's 2 and 2/9.
Yeah. And then when we move on to the next one, we're at 24/9. 24/9 is 2 and 6/9. So this guy here is going to get 6/9 of the pixels colors, and this guy is going to get 3/9 of it. Okay. And then when we get here, it's exactly even, maybe? We're at 28. No, we're at 28, so it's going to get... yeah. Do you see that, though? So when you have a fraction left over, you have to split the pixel value between the one above it and the one below it. And as you go along, the pixel values will accumulate upwards until you hit a whole number, then you move the thing up. Subpixel animation, yeah. Yeah, anti-aliasing is kind of a broad and big topic, but this is one way of doing it. There's a lot of line rasterization algorithms out there. There's a lot that use assembly for, like, back in the day. They basically would accumulate fractions as they move along, and when they hit a whole number, they move up a row, and then start accumulating fractions again, and then they draw 2 pixels as they go across to do a nice anti-alias line. And somebody, I think Bresenham is the name of the guy that did it, had a Bresenham algorithm, had a very fast implementation assembly. Or maybe Bresenham's doesn't do anti-aliasing. Let's see here. Wu's algorithm. Yeah, there we go. So I'm thinking about Wu's algorithm then. So you can see as it goes along, you see how it like accumulates more darkness as it moves down, and then it drops to the next row. So this creates a nice anti-aliased row here. So Bresenham doesn't do anti-aliasing. Okay. So yeah, if you just do whole numbers, then you just accumulate fractions till you get to the next row, and then you move up. Okay. Now, what circumstance will this algorithm not work on, Isaac? So we've got essentially Wu's algorithm here or something like that. I don't know. We built it ourselves. We'll call it the Ship-Kearney-Collins algorithm. Uh, what circumstance will this algorithm not work? It'll completely break. Collins, do you see it too? Our algorithm has one giant crucial Achilles heel in it. Do you know what it is? What circumstance will our ship Kearney Collins algorithm just die? It will probably crash even. Vertical line, exactly. What's the slope of a vertical line? It's a tough one, right? And, you know, if you, your for loop will start at x is equal to 0, finish at x is equal to 0. So it's just going to draw one dot on the screen, you know, if it doesn't segfault or something, or division by 0 or something, right? Even if you handle that or something somehow, it's going to draw one dot on the screen, not a vertical line. And maybe we can ignore vertical lines for now and just kind of give maybe a bigger illustration of the problem. Let's start with x is equal to, we'll just start at 0, 0. We'll just normalize to 0, 0. And then we'll go 1 to the right, 2 to the right, and 10 up. It's got like a Cartesian coordinate system or something like that. Fancy, whatever. Okay, so this is at location 2, 10. Okay? So how will our algorithm work here? Well, the rise over 1 is 5, right? So when we go to x is equal to 1, y is equal to 5, x is equal to 2, y is equal to 10, done. Here's our line. Dot, dot, dot. Is that a very good line? No, it's not a line.
What are you trying to call a line?
We're trying to draw a line between this point here and this point here, but all we do is we put one point in the middle and we're like, we're done. That's a line.
Excuse me?
Is that a line? It's not really a line.
Oh, I thought you were talking about this line.
No, these are the axes. I kind of drew like the y-axis up here. This is the y-axis.
You want me to make a line for you?
No. We're trying to figure this out. We're doing the powers of programming by thinking about how it can break.
Okay.
So, and this will get even worse if you know, like the destination was like up here, right? It wouldn't draw any points in between at all. It'll draw the starting point, it'll draw the ending point, and nothing in between. So, how do we fix that? We got two smart programmers on here. How do we solve the problem? Because our algorithm is going to work fine, actually, when we're like in the, here's like a 45-degree angle. As long as our final point's over here, we're going to get a nice connected set of points, right? It's actually going to draw a contiguous set of points from point A to point B. But once you are sort of outside of this 45-degree arc, and this extends down this way as well. So once you're outside of this quadrant, all of these points up here is the fail zone, all right? So our algorithm is just not going to work anywhere up here, and it's also not going to work down here as well. This is also the fail zone, okay? So our algorithm works fine here. Our algorithm works fine. Actually, it doesn't work fine over here because our for loop assumes x plus plus, right? So we actually have a fail zone over here as well. Our algorithm only works on 1/4 of all lines. Now, we can make this work by just switching the starting and ending point, right? So that the starting point's to the left. If the denominator is 0, they do a for loop that draws upwards, but that's good. But parameterizing it's also good. Those are actually two good and separate solutions. So one way of doing it is to parameterize the line, right? So if you have the line like this is a line that is 0 in the x direction and 1 in the y direction, and you can simply iterate in that direction every step until you get to the destination, right? That's one way of doing it, which is y is equal to t times you know, some vector or something like that. So you have a vector, and t is the number of steps, and y basically the distance. So y is the distance from this, and we're assuming we're at the origin again to make life easy. And so you can parameterize it. Absolutely, you can definitely do it. A lot of code in 3D graphics are using parameterized line equations like that. Collins, does that make sense to you? Isaac's explanation, basically, rather than having a slope, you define the you simply have a direction, and then you just keep stepping in that direction 1 pixel at a time until you hit the end zone, right? And t actually usually ranges from 0 to 1. So t usually goes from 0 to 1 when you do these line equations, and 1 is at the destination, 0 is at the origin, and then you just sort of loop along the way, or you just do a for loop that says, however far apart it is, and just draw all the pixels in between. Now, Collins' approach is another approach that will work, and that is to flip the loop around. So rather than looping on x's, you loop on y's, right? So you just say, if you're in the fail zone, write the other for loop. For int y equals 0, y is less than or equal to, in this case, 10, y plus plus. Oops. Running out of room over here. Make it a little easier to read. So starting at y is equal to 0, as long as y is less than or equal to 10, y plus plus, draw a pixel, however that works, equal to y is the backside, and then on this side, what do you put in for x? What goes there? Like that, right? And we have normalized to 0, 0. So it's just going to be y divided by m and y. Or you just, and you can compute this slope the other way as well. So it's basically the exact same algorithm. You just reverse the algebra, right? And so rather than iterating on x, where you go x is equal to 1, x equals to 2, x is equal to 3, which gives you this really broken line, and it gets more and more broken the more vertical it gets, what you do instead is you iterate over y. And so you say y is equal to 0, y is equal to 1, y is equal to 2, y is equal to 3, and you compute the value of x as you go along, and then you end up with a nice solid line that way. And that is your homework assignment. Okay, so your homework assignment is to do that. So given a starting point, an ending point, draw a line between them. And I have on the server a header file that allows you to move the cursor to a certain location and draw a pixel there. Okay, let me show you how that works. Ranges sort. That's cool. So let's say I want to draw a line on the screen for int, and so what you're going to do is you're going to int x is equal to x1 is equal to read. Please enter starting x. Okay, so you got starting value for x, starting value for y, any value for x, any value for y. Okay, and you want to draw a line between them. This is your homework assignment. Okay, So I'm going to give you the easy part. All right, so we're going to say well, I'm not going to handle the fail zone. That's actually your homework assignment. So I'm just going to assume that it's in the right quadrant, basically, that 90-degree area to the right. I was going to start fixing it and doing error checking, but I'm not going to. That's actually your assignment. Okay, so we're just going to do this for int x equals x1. Let me pause this. Third time they've called me. Nope, it was an auto warranty spam. Okay. All right. X is less than or equal to x2. X plus plus. So we're starting at x1, going to x2. So it's this circumstance here. We're starting at x1, going to x2. You guys with me so far? No video. Oh, okay. How about now? You guys with me? For int x equals x1, x is less than or equal to x2, x plus plus. So we're going to start at x1, go to x2, and then we're going to figure out the y value along the way. We're going to have a draw pixel function that will take an x and a y and a color, maybe. Should we do a color? Why not? Okay, so we're going to take an x and a y location and a color, and we're going to draw a pixel there. So move cursor to row, and row is y. Column is x. And we're going to clear the screen first, of course. So these functions are all found within my colors.h library. So move cursor moves the cursor to that spot on the screen. So we clear the screen first, and then we're going to draw a pixel there. And so we're going to set the color. So we're going to say set ground color to be R then G then B. Okay. So we're going to set the color to be whatever color is passed in, and then we're going to see out a space. Okay. Flush output buffer. And so whatever x and y location you pass in and color, it'll draw that color pixel at that location. Okay. And then when we're done, we should probably pause or something. So, char x equals read. Enter anything to. Okay, so here is the algorithm. So there's the code to draw. There's the code to do the input. Now we're going to do the meat of the program, less, all the different ways it can break vertical lines, going to the left instead of the right, that kind of stuff. Okay, you guys ready for this? Ready to see some algebra in action? You guys good?
Not brain dead zombies.
Not brain dead zombies? Excited? All right. I'm not doing the Wu's algorithm. I'll just do Bresenham or something like that. Collins ship. All right. Here we go. All right. So we are going to draw pixel. Or, let's do some math first. Make the math a little easier on us. So the y location is going to be equal to our starting y location because I'm not normalizing it like I said I would. Our y location is going to be equal to our starting y location plus how far to the right we've moved from x. So int run is equal to x minus x1. That's how far to the right we've moved. And then y is going to be equal to the starting y, y1, plus y is equal to mx plus b. So our starting y, then we move 1 to the right, we're going to move m up. And so this is m. No, it's not m. The slope, let's see here, is equal to y2 minus y1 divided by x2 minus x1, and we need to make you a double, so we don't round down to 0. And there we go. So that is the run. No, that's the rise, that's the run. This is the slope. Okay. So mx plus b. And there we go. So draw pixel. Got x, we got y. For R, G, and B, we will do random colors. Why not? Let's do rainbow, rand, modulus, 5. Dang, almost worked. And then what are we missing here? We need a semicolon. Okay. So I'm sure this will work right the first time. Let's give it a shot. G plus, and let's succeed. Starting value of 10. Any value, starting value 10, 20, 20. There we go. So starting at 10, 10, going to 20, 20. Remember 0, 0 is the top left corner of the screen. We have a nice rainbow colored line. Okay. And then we should probably move the cursor back or something like that. And reset the colors as well. So move cursor to 0, 0. Move it to the top left corner of the screen. And anything to continue. Reset the colors because the colors are going to be all screwed up. And then clear screen. And then end. Okay. Time. Starting value for x. 20. Starting value for y. 20. Going to 40. 40. And it went off the bottom of the screen. Oh. One more time. 10. 10 to 30. 30. There we go. Got a perfectly nice line. And anything to continue. There we go. Okay. Probably should reset the color before we print that. One more time. 0, 0 to 20, 10. And you can see we have a more horizontal line this time. Okay. Got some random numbers in here that are black, but yeah, there you go. Okay. 2 to 40, 10. So there you go. Works fine. Until we do a vertical line, right? So try and do a vertical line. For 20, you can see it's just like I told you. You get this broken line. Boop, boop. Right. So your homework assignment is to implement Bresenheim's algorithm. Bresenham's algorithm.
My computer crashed.
No crashes.
No, not just like my whole computer.
The whole computer crashed. Yeah. It's, Windows be like that sometimes, girl. I'm sorry. All right. You guys think you can do it? Handle vertical lines. Handle.
There we go.
Handle the zone of failure. So this code is this right now, without doing the anti-aliasing. And then you need to handle the fail zone because currently 3/4 of all possible lines won't work. All right. So. Okay. What if the line goes backwards? What if the line goes vertical up? Line goes vertical down. So backwards is pretty easy. If the starting point's to the left of the other point, you swap it. Right? Just swap the points. But that's it. I mean, that's line rasterization right there. So, okay. toss this into directory maker line. Minky line. Okay, that's our class for today. And then maybe we'll do anti-aliasing next time if that interests you, and then we'll move on to triangle rasterization. I'll type up the README file for it, but I'll push it out for you guys in a few minutes, and then that's it. Okay, shouldn't be too bad. Could be annoying. It could be annoying if you don't have especially if you're like me and just test like normal lines, you forget lines can go backwards and things like that. Then bugs can creep into your code. But that's the general gist of it, is that you need to flip the y and the x around, and you can either do Collins' approach, where you loop across the y's instead of looping across the x's, or you take Isaac's approach and parameterize the line equation, and then just step in the direction of the thing. Just make sure you handle Isaac, the person starting and ending on the same spot, because then you will get a 0, 0 for your direction and might, explode as a result of it. You gotta handle the edge cases. Okay, so that's it for today. Thanks for coming out. I hope you guys had a good time, and I'll see you. You'll use the other one. Yeah, either way, they're honestly, the parameterized is probably more commonly used, just because it handles vertical lines, right? And so you don't have to special case them every time. It is easier. You're going to take the exact same code, and you're going to do an algebraic transformation. Y equals mx plus b turns into y minus b divided by m equals x. Just do a little algebra, good to go. Should not be too bad. All right, so that's it. Thanks, guys. See you tomorrow.